En la agenda lo tenía a las 10 de la mañana y estaba yo haciendo hasta tiempo en la oficina para llegar acá. Así es que me disculpo, fue un error administrativo. Pero bueno, ya después de esto quisiera darles la bienvenida en este workshop. Estaba yo leyendo, fue cuando me di cuenta que era las 9:30, porque empecé a leer el programa y decía sobre como la manifestación macroscópica de la mecánica cuántica, ¿no? Y tenía ahí una pequeña descripción. Y bueno, yo también me dedico a eso de alguna forma, yo hago estado sólido y no es otra cosa también más que la manifestación macroscópica de la mecánica cuántica. Y pues me da mucho gusto, ¿no?, que estén aquí, que tengan este workshop. Welcome, benvenuti, buongiorno. Y pues de verdad les deseo que sea muy fructífero. Otra vez una disculpa, realmente me apena mucho, se ve poco profesional esto, pero bueno. Y pues gracias Jorge y a todos ustedes, a todo el departamento de cuántica y fotónica, de física cuántica y fotónica, por hacer este workshop y que tengan una feliz jornada. ¿Sí? Bueno, gracias a ustedes.
Ok. Bueno. Pues muchas gracias a la doctora Nogués por aceptar venir a la inauguración del evento. Entonces, como ella ya lo dijo, el tema del workshop es presentar resultados novedosos en el estudio de fenómenos cuánticos que se manifiestan a escala macroscópica. Y básicamente la idea de este tipo de fenómenos es que un número muy grande de partículas ocupa un único estado cuántico individual, y entonces por ese motivo las propiedades macroscópicas aparecen a escala macroscópica. Entonces en este workshop lo que hemos buscado es presentar resultados novedosos en esta área desde diferentes perspectivas. Por un lado, uno puede tener sistemas cuánticos macroscópicos hechos de materia, de átomos, o hechos de luz, o de bosones, o de fermiones, o de sistemas que no interactúan, o de sistemas que interactúan muy fuertemente. Y cada uno de estos aspectos, aunque tenga cada una de estas diferentes sistemas, aunque sean muy distintos y muy diferentes en su descripción, comparten esta idea de un único estado macroscópico que describe a todo el sistema. Entonces, vamos a dar inicio al workshop, pero antes de eso quisiera hacer algunos agradecimientos. Por supuesto quiero agradecerle a la directora Cecilia Nogués por darnos la oportunidad y el espacio de organizar el workshop, a toda la administración del instituto que nos ayudó muchísimo con la organización y la difusión del evento. Quiero particularmente agradecer también a mi equipo, a mis estudiantes, al doctor Jackson Poveda, que también han estado trabajando muchísimo, ayudándonos a la organización. Y por supuesto, agradecerle a todos los invitados que aceptaron venir a dar una conferencia. And at this point, I will switch to English, because at least the first conference will be in English. Okay. And I would like to start presenting Doctora Patricia Castillo. So, Doctora Castillo, well, I met her many years ago in Brazil when I was doing my PhD there. She was just an undergraduate student, and since then we started to work together, setting a new experiment on Bose-Einstein condensates. And now, well, later she finished her undergraduate thesis, then she moved to the master in the same place in Brazil at the Institute of Physics of São Carlos, University of São Paulo. She got her master degree and her PhD degree there. Her PhD degree she made a a sort of cooperation with Italy in the University of Florence and Laboratorio Europeo de Espectroscopía No Lineal, where she made some measurements. And since July, right, she is a full professor at the University of São Paulo, and she's setting a new experiment in probably 2D physics of quantum macroscopic systems. And today she will be presenting a talk concerning what she did during her postdoctoral internship in France concerning two-dimensional Bose gases. So, okay, Patty.
No? Alô? 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 Sim? Foi? Sorry. Okay. I think it's working. Yes?
Yes.
Okay. So let me just. Yes. So it's a great pleasure to be here and finally visiting Jorge Lab. So as he told you now, we met many, many years ago, about 13 years ago, so really a long, long time. So I'm really glad to be here, and I would like to thank you for this nice introduction, and thank also the organizers for putting together this workshop, that I'm sure it will be a very nice event. So what I want to talk to you today is about part of the work I did during my postdoc in France in the group of Professor Jean Dalibard, in which I worked with uniform 2D Bose gases. And here I want explicitly to tell you about the dynamic symmetries of such systems. Okay? So systems that exhibit symmetries are interesting because symmetries are always behind conserved quantities of these systems. So if we have a system which has a spatial symmetry that is associated with the translation and the rotation of the system, we have that both the linear and the angular momentum are conserved. But so these are the usual symmetries we learn in basic courses of physics, but there are also another class of symmetries which we call dynamical symmetries that will involve transformations of these systems in both space and time parameters. Okay, and these transformations will leave the action of the system or the equations of motion of the system invariant. So we can give one example of a simple system that shows both class of symmetries, which is the Kepler problem. So if we have two rigid bodies that orbit one around the other, as the Sun and the Earth, and this movement is governed by this equation of motion, in which the force acting in these two bodies is simply the gravitational force, we can see that these kind of systems have a rotational invariance, which leads to the conservation of angular momentum, but it has also what we usually call hidden symmetry, that is the conservation of the Laplace-Runge-Lenz vector, which means that these orbits are closed and the energy of the system is always smaller than zero. And this hidden symmetry constitutes a dynamical continuous symmetry of the problem. Okay? So now, if you have a system that has a dynamical symmetry, there is a special class of these systems in which they have this scale invariant property. This scale invariant is pretty much when the system the equations of motion of the systems are invariant under a dilation transformation in space and time, which are given by this set of two relations here. So if, for example, you have a collection of non-relativistic particles that do not interact, you can show that if you apply this kind of transformation, the kinetic energy of the system will rescale with this lambda parameter square, and the action of the system, which is proportional to the integral of the kinetic energy over time, is left invariant. Okay? So now if this system interacts, and the interaction energy is also rescaled with the same scaling parameter, then the system is said to be scale invariant. And such systems, they are interesting because they have very simple thermodynamic properties. For example, the equation of motion of these systems, the equation of state, sorry, of these systems depend only on the ratio of the chemical potential over temperature and not on these individual two parameters. So this simplifies a lot the thermodynamic description. So the examples we have, some examples we have on scale invariant systems are this collection of non-relativistic particles, either that are not interacting or that have interactions described by 1 over r squared potential. Also, the 3D Fermi gas at unitary regime is also a scale invariant system. And finally, the weakly interacting two-dimensional Bose gas also show this property. So here what I'm showing you is the equation of state measured for a weakly interacting 2D Bose gas in the group of Cheng-Xin. And even for different, so here in the inset, I show you the density profile of different clouds at different temperatures with different chemical potential. So they look very different, but once you calculate the rescaled equation of state, you see that you reach a universal behavior in which all the curves overlap into a single curve, okay? So in this work, what we want to do is to go beyond these static properties of these scale invariant systems and look the dynamics of a 2D Bose gas in a harmonic potential. So all the results I will show you have been recently published on PRX. So if you want to take a look afterwards, you can just follow this reference. Okay, so here I come to the outlook of my talk. So I divided in two big parts. So in the first part, I will show you the results I just introduced you before. So I start first describing the experimental setup. Then I enter on the dynamical symmetries that these systems are related to. And I show you 3 experiments we perform in order to show to prove the dynamical symmetry we associate with such systems. And in the end, I finish discussing a bit the observation of two-dimensional breathers. And on the second part, I want just to introduce to you the Brazilian group I have recently joined as a permanent member, just to give you a flavor of what has been done in Brazil these past years, okay? So the experimental setup is quite simple. We want to produce a uniform two-dimensional Bose gas of rubidium-87 atoms, and in order to do so, we use the usual steps for cooling and trapping rubidium atoms until we reach a Bose-Einstein condensate in 3D, made in a crossed dipole trap. So here, there is a problem. Okay, it's not appearing all the image here, but this is supposed to represent this 3GBC, and here it should have a glass viewport up and down, but it's not a big deal. Okay. So then once we get this BC, what we do is that we load these atoms into a vertical optical lattice with tunable confinement along the vertical direction that goes from 2 to 5 kilohertz. Later, we switch on the in-plane confinement using a digital micromirror device that is drawn here in order to create a box potential and produce clouds with uniform density. So this digital micrometer device, it's nothing more than a set of array of micrometers that are controlled individual to two positions, on and off, such that you can shine light to the direction of the atoms, or not, you can shine to another place. And you can draw anything you want with these micrometers, such that the atoms will accumulate in the dark regions of this DMD. So now, if I cool the atoms down to the generate regime and I perform an absorption image, what I see is this image here, in which I produce a uniform cloud with the shape I put on my DMD. Okay? So as I told you, we can do many, many different shapes. So here I show you some other shapes we have produced in the lab. So these are all absorption images of the atomic cloud. And this shows you the large flexibility of this kind of two-dimensional potentials. Okay? But in all experiments I will talk to you today, what we do is once we evaporate the cloud into the degenerate regime, we switch off this box potential and we let the atoms evolve in a 2D harmonic potential produced by a pair of coils in anti-Helmholtz configuration. And the frequency of this harmonic trap is of about 20 Hertz. And we let the atoms evolve for variable times in order to later take an absorption image and study the dynamics of this cloud in this harmonic potential. Okay, so now before entering on the dynamical symmetries that we have associated with these systems, we need to know how to describe these two-dimensional clouds. So as I just explained, these 2D clouds are produced from 3D gases that are strongly confined in one direction of space. So usually this confinement is made with a harmonic potential, so we use an optical lattice. And if h bar times the frequency of this strong confined direction is much larger than the thermal energy of your system, you enter in the quasi-2D regime, in which the scattering properties of your system are modified by the strong confinement. So it appears here, this LZ term, that is the oscillator length of this strong confined direction. Okay? So now if we are dealing with weakly interacting atoms, such that the scattering length is much smaller than the oscillator length LZ, the interactions are mediated by a dimensionless parameter, G tilde, that is given by this relation here, such that we can describe the interactions of the atoms as a mean field approximation. Okay? So in this case, the description of the gas can be done by means of a classical field that evolves according to a Gross-Pitaevsky equation that is written here in this form. It's also in this context that, so I don't know if all of you are familiar, but Bose-Einstein condensation do not happen in a purely 2D system, but you have a transition to a superfluid state, and it is in this context that this transition happens via a BKT phase transition, which occurs for a critical phase density given by this relation here that will depend on the G tilde parameter I just defined. Okay. So now that we know how to describe this kind of systems, we can try to look for the symmetries that are involved on this problem. So I will start first with the free cloud, such that the external potential is set to 0, and we have a simpler Gross-Pitaevsky equation here without any external potential. So in this case, we can see that the transformations that leave the equation of motion, the Gross-Pitaevsky equation invariant, are given by a time translation, given with this relation here, Also, we can look for the dilation transformation. I told you on the introduction that we'll modify space and time with these two relations such that the wave function is modified by this relation here, and the kinetic energy will keep its scaling with the lambda square parameter. And now, if we look to the interaction energy of these 2D gases, defined as this equation, we see that also this interaction rescales in the same form. And yes, the system is really a scale invariant system. Okay? And there is also another set of transformation that we call expansion that will change both time and space in such a way. And if we combine these three sets of transformations with the usual Galilean transformation of space, we found a general formula for all transformations that leave the Gross-Pitaevsky equation here invariant. Okay? So now, once we know we have this general formula, we can ask ourselves which is the symmetry group, if there is a symmetry group that is associated with these transformations. And in order to do so, what we do is we look to the infinitesimal generator for all these possible transformations, and we find these three generators here, A, LB, and LC. And after some linear combination of the three, we can define L1, L2, and L3 that show this commutation algebra I'm written here, okay? And this algebra is the same of the Lorentz group SO21 symmetry group. So we can associate the properties of this group to our system. So I didn't do all this calculation here, it's quite long, but if you are interested, you can take a look on these three papers here. So the two first are for two-dimensional systems, and this last one is 3D Fermi gases, okay? So, good. So now we know how is the symmetry for the free cloud. Now I told you I want to study the dynamics of the system in a harmonic trap. So if I look for the case in which I add a harmonic potential to this Gross-Pitaevsky equation, I can first take a look on the dilation transformation I just told you before. And we see that even though the kinetic and the interaction energy rescale in the same way, the potential energy rescales now in a different way. So the system actually is no longer scale invariant once we put this system into a harmonic trap. However, there are a set of transformations that leave this Gross-Pitaevsky invariant, and we can show also that these transformations can be associated with the same symmetry group as SO21, and we can use again, the properties of this group to describe our system. So this you can take a look on, So this you can take a look on the supplementary material on our paper. We do all the calculations in order to prove that even in a harmonic trap, we have the same algebra. And this algebra is very interesting because it has a very strong consequence on the evolution of the potential energy. So the potential energy will oscillate in time with 2 times the frequency of the harmonic confinement, okay? And this has been observed already on these 2 papers I list here. And we also observe this on our experiments. So what we do, we start with a uniform field square, like this, and we let this square evolve. So we prepare it in the box potential. We switch off the box potential, and we let it evolve in the harmonic trap only in 2D. Okay? And what we see is this set of images I'm showing you here, and we can calculate the potential energy with this expression here directly by numerically integrating the density profile. And we obtain this graph that we clearly see this oscillating behavior of the potential energy. And once we fit these experimental points, we get a frequency of 38.5 hertz while the trapping frequency is of 19.3, so it's in very good agreement with what we expect. So now there is another thing I can point out from this data. So even though the potential energy oscillates in time, we see that the shape has very different shapes up here. And if I look only for the images in which I have the same potential energy, I see that I have no restrictions on the shape of the cloud. I cannot really predict what will be the shape of the cloud I will observe for each potential energy, even though they have the same potential energy. Okay, so I will go back to this at the end of this presentation when I discuss the two-dimensional breathers. It's just for you to keep it in mind. Okay, so now that we know which is the symmetry group associated with these systems, we can use the symmetry group to link two different solutions of the Gross-Ptaevsky equation and map their behavior. So this can be done, for example, keeping the interaction energy of these two wave functions, PC1 and PC2, the same, and also making this cloud evolve in the same harmonic trap. So if we do this, and we use all the algebra we knew from the SO2 symmetry group, we can have a general formula for the rescaling of time that is going to be here on this eta parameter, and the rescale on position. Okay, such that if I have a PC1 that is a solution of this full Gross-Ptaevsky equation, this PC1 will be mapped into a PC2 that will be rescaled by these two relations here by this rescaling function f, the r and t. Okay. So in the experiment, we can simplify a bit. So what we have is that we have special conditions for this mapping of RT into R prime and T prime. And we want to map T equals 0 into T prime equals 0, so the same initial time. And we also start with a cloud initially at rest. So we prepare it in the box potential and we switch off, and this cloud is at rest, and then it starts to evolve in the harmonic trap, which makes the derivative of this lambda parameter at the initial time equals to 0. And this simplifies this relation here for alpha, delta, beta, and gamma, such that beta, gamma, and gamma are equal to 0, and delta is equal to 1 over alpha. If we use this simplification, we change this general formula, like these new relations I put here in orange, and we can use them to try to map the evolutions in the experiment. Another thing we can do, we can go a bit further and try to connect the evolution on two different harmonic traps. So we can do this by adding a new parameter, zeta, which will rescale these trapping frequencies. And then with this, we can see that changing on the change on the harmonic frequency is just a dilation transformation in which the position is rescaled like this, and the time is rescaled like this. So if I add the dependency of this zeta parameter into this general formula, I get this final set of equations in which I put the zeta parameter here in orange for you to compare with this previous formula I showed you. And this we can try to see on the experiment. So this is what we do now. So we want to link the evolution of two wave functions at different trapping frequencies. So we start with the same cloud, a uniform field triangle with side equal to 40 micrometers. And here we have 4 × 10⁴ atoms in these two clouds. And we want to compare the evolution with omega 1 equals to 0, which means that the cloud evolved freely in the 2D plane, with the evolution in the harmonic trap with frequency of about 20 Hertz. So if I do this, okay, so with this set of parameters, actually the rescaling in position, in size, is the same. So alpha, the alpha parameter is 1. And since I want to rescale a free evolution in 2D into this harmonic trap, this zeta parameter tends to infinity from the previous relation I put it here, okay? So this zeta parameter tends to infinity, which modify a bit the scaling relations I had before. So I have this final two relations here that I can try to observe in the experiment. So if I left the cloud evolve in these two different harmonic potentials, I observe this sequence of images, and we can try to see this scaling relation pretty much calculating the overlap between these two density profiles, okay? So how we do it, it's a bit complicated. So we define this P parameter in which I choose one image of the first set of evolution, and I calculate it for all the images in the second set, changing this lambda parameter that will rescale the first density profile in this form, okay? So here I have for each combination of images, N1 and N2 and 2 and 2, so I calculate, I have many values of lambda in order to get later the maximum of this P parameter with respect to the lambda I'm using. So this I define as the overlap between the density profile N1 at T and N2 at T prime. And actually, in order to see these scaling relations, I want to see the optimum value of this overlap. So the maximum value of this overlap with respect to T prime, to see which is the image that matches better the shape that for the image I choose on the first set of images. Okay? So then I define this lambda T as being the value lambda from the maximum value of this overlap with respect to T prime. And if we now plot these things, what we see is that this is omega times T prime, and here is omega times T, that is the first scaling relation I have here. Okay, and these are the experimental points, the circles, and the solid curve is this equation with no free parameters. So the theory matches very well our data, and this is also the case when we look for the lambda parameter here. That is the second one. Okay, so we can clearly describe and map the evolution of these two wave functions done at two different harmonic potentials. Okay, so now the question is, can we go further? So far what I can do is change the harmonic potential and change the size of the system, is the two things I can do. But can we go further? Can we, for example, map the evolution of two wave functions with different interaction energies? And the answer is yes, we can, if we go to the hydrodynamic regime. So if we write the Gross-Petaevsky equation now in terms of the density and the velocity fields, which is the hydrodynamic equations, we can use the condition that the healing length of the system is much smaller than the size of the system, such that we can neglect this last term, which is associated with the quantum pressure. And by doing this, we can find a relation to map the two wave functions with different interaction energy. So I introduce another parameter here, mu, that will rescale the interaction energy here. And with this new parameter, we get this set of equations for rescaling time, position, and the atomic density. So here I put the mu parameter in orange to show you that these relations are very similar to the ones we used before, but with this additional parameter mu. And instead of looking only to the wave function of the system, we have to rescale it using the interaction parameter G tilde also, okay? So in our system, we performed 2 experiments, which we present on the paper, but here I will focus only on the second one, in which we change both the interaction energy and the size of the system. So what we do is we start with a uniform field square with different sizes. So the first one has a size of 27 micrometers, the second one has a size of 37 micrometers, and different atom numbers. And we let it evolve in the same harmonic potential in order to observe this series of images. So now, if we look by eye, you can see that these 2 images that look more similar between each other, they are dislocated in time, as we also expected to be, since we have to rescale both the position and the time. Okay? So in order to analyze this data, we do the same method of calculating the overlap, and what we obtain are this set of graphs here, in which I show the rescale in time in the first graph, and the rescale in size in the second graph. And this, again, the solid lines are the theory, so the relations I showed you in the previous slide. So these relations here, with no free parameters, and we see that they match quite well the experimental points. And this, so once we are in the hydrodynamic regime, actually what we observe is a universal behavior of the cloud in which we can change any parameter, the atom number, the size, the interaction parameter, the harmonic confinement in which this cloud evolves, and all these changes can be mapped into a universal behavior. So this is quite nice. Okay. So now I enter to the last part of this first part of the presentation, in which I discuss a bit the 2-dimensional breathers we observed. So far what we did is we could link the evolution of 2 different wave functions, PC1 and PC2, given the fact that we vary all parameters, and the interaction energy we can vary only on the hydrodynamic regime. We also saw that the potential energy has this periodic evolution with frequency of given by 2 times the frequency of the harmonic confinement, but there were no constraints on the evolution of the shape of the wave function. So if you remember what I showed you before, we started from a uniform squared field square, and we see that it evolved like this set of images here, and we see that this evolution is not periodic. So the shape of the cloud is not periodic, which means that the wave function describing this, this cloud do not evolve periodically neither. So, but is it true for all shapes? So what we did is we tried with a triangle, a equilateral triangle, and we look how it evolved in time. So is there a period we can relate to the evolution of the shape of the cloud? So we can take a look on this GIF, and we clearly see that we starting with a triangle that points downwards, I think. Yes, it goes upwards and downwards and upwards and downwards. So it's really periodic, the motion of the atoms when we start with an equilateral triangle. Okay, so I just show you here the first images of that GIF I showed you before, and here we can also calculate the overlap of each image with the first one in order to see if we see a oscillatory behavior. And indeed, we see oscillatory behavior that goes down, which means that the triangle that was pointing up downwards points upwards, and then it goes up again, showing that the triangle points downwards again. And it's quite uniform, as we can see already by the images. Okay? So this behavior is what we call a breather. So this is what we call a 2-dimensional breather, and it's a wave function, psi, that evolves periodically according to the Gross-Pitaevsky equation. So there are other breathers that we can list here. So the simple case of a breather is the steady state of the system. But in 1D, for example, if you go for parameters smaller than 1, a bright soliton is a breather that evolves periodically in time in this kind of systems. And here you have a reveal on this kind of bright solitons in 1D systems. Okay, so then we did also a set of numerical simulations in order to see if it was true that after T/2 we recover a uniform field triangle, and these are the images we see from the numerical simulations, and we calculate here again the overlap of the first one with the following ones. And here I showed you this overlap. So I showed you the difference of this overlap with respect to 1, which would be a perfect overlap. And we see that it's very small. And as we approach the hydrodynamic regime, this value decreases even further. So yes, we see also the same kind of behavior on the numerical simulations. But actually, we cannot explain it, why it happens. And we tried many different shapes. So I don't have all the GIFs here, but we tried the square, the pentagon, the hexagon, a star, a right angle triangle, and we see no periodic evolution of the shape of the cloud. We see for the triangle, and maybe for the disk cloud, a circle, which period that is equal to 2 times the period of the harmonic trap. And this result is not completely clear on the experiments, but it's quite robust with the numerical simulations. So here we have many open questions. So since we cannot explain this behavior analytically, we have these many questions. So the first one is why we get a different period for the triangle and the disk. And also, is there a way of proving this breather mathematically? Can we do it analytically or not? And are these breathers linked to the dynamical symmetries I just showed you before? In this case, if they are linked, there will be also breathers for interactions described by 1 over r square potential, and also for 3D gases, Fermi gases in the unitary regime that we don't know which will be the shape, but they will be there. And are these breathers resilient to an increase of this G tilde parameter? So we will see some effects of quantum anomaly that is due to the fact that actually we are only in the weakly interacting regime, and we have a logarithmic term on the interactions, on the atomic interactions, once we departure the weakly interacting regime, increasing G tilde. So all of these are open questions for these two-dimensional breathers that we could not yet answer. So, okay, so this is always a teamwork. So here is the team of the rubidium team. And most of the work was done by this guy here, Rafael. So he just finished his PhD now in September, and his thesis is very complete on this subject. He do all the math. So if you want to take a look, I think soon it will be online, and you can look. It's really good. Okay, so now I go to the second part that it's a bit more relaxed. So I just want you to give a flavor of what the Brazilian group, I did my undergrad students and PhD, and also Jorge and Fred did their PhD. And now I'm back there as a professor, so I want to give you the idea of what they do there, and yeah. So it's I'm back to Brazil, so in the University of São Paulo, in the Physics Institute of São Carlos, which is a city in the countryside of São Paulo state. So here there are two pictures of the campus of the university, which is quite nice, quite sunny. And this is the atomic physics group, so we are part of a bigger group, the CEPOF. So here is the link to our website. And the atomic physics part of this group has 3 professors. So Professor Bagnato, that is the group leader of all the CEPOF, actually. And he has 2 experiments. One, a rubidium BC experiment in which he performed some studies on thermodynamics in collaboration with Victor Romero here, and also on quantum turbulence. There is also a second experiment on mixture BC with sodium and potassium, in which they want to study miscibility effects and couple vortex lattices in such a mixture. So the second professor is Philippe Courtet. He works with strontium atoms and he has 2 labs, both working with light and matter interaction in a cold cloud or with atoms in a cavity, in a hyphenous cavity. And there is also Professor Emmanuel Hein that is building up an experiment with dysprosium atoms. So it's in the early stages of the experimental setup. And now I have recently joined this group. So, and the idea is to try to implement a 2-dimensional system with potassium atoms such that we can tune the interactions, which is a new ingredient to all the physics I discussed to you today. And at the beginning, I will be involved in these 2 experiments as well as a collaborator with Professor Bagnato, that was also my PhD advisor. So we already collaborate before. Okay, and to finish, I just want to say that we are organizing a school on April, and in which we are going to talk about many important aspects on the field. And there is a very long list of speakers with very important people as Bill Phillips, Ronald Hewlett, and Stringari, Kleppner. So if you want to try to apply for this school, do it, because we have grants also for bringing students. So yeah, it's a limited number of positions, but we have grants. So if you are interested and motivated, go to this website and do your subscription. Okay? So that's it. Thank you very much.
Thank you very much for your very interesting talk, Patricia. We have actually plenty of time for questions. So, Víctor? Okay. Después
Well, thank you. No, it's just a simple question or comment, because you find this with this triangular symmetry, and I can figure out that the pentagonal and the star, you break a lot of symmetries and you cannot have in 2-dimensional. But the square one, I don't understand why you don't have this periodic. Do you have some idea, something? Because the pentagonal and etc., of course, no, in this 2-dimensional, probably you don't have that symmetry. But the square is, you don't have any...
No, we have no idea why
about that.
The triangle is so particular, and we observe this clearly periodic evolution. This we really have no idea. No idea. We try to find some explanation, but analytical one, but we didn't manage. So that's why we did the numerical simulations, because we thought at the beginning it was an artifact of the experiment. But no, doing the numerical simulations, we don't see this behavior for any of the other shapes. We only see the behavior for a triangle with this period equals to T/2. And for a uniform disk, we see, but with a different period. But it's not clear on the experiment.
Because you can push, for example, with this extra term that you have the Gross-Pitayevsky equation, you have the R squared, no?
Yes.
And probably you can break the symmetry there, or to induce some kind of symmetry and try to...
Yeah, so
I don't know if you
Yeah.
try it or something.
even
It's,
with the harmonic potential, so we have a symmetry, a well-defined symmetry for the system, which is this SO21 Lorentz group for the symmetries, and but these do not explain. So these do not put any constraint on the shape of the wave function. These do not.
Okay.
So the only constraint that it input is on the evolution of the potential energy, and then you can relate different wave functions into one another. This you can do with the use of the symmetry, but if you don't have a first evolution, you don't know how it will evolve. So you need at least one to know the shape, and then you can construct any other evolution that you want, and you know how it will behave. But if you don't have a first one, you don't know how the shape will behave. There is no analytical prediction, no analytical restriction that will say, okay, from a square it will evolve like this. No, and neither for the triangle.
Okay, thank you and congratulations.
I think you essentially answered my question, but still just a little bit more in the you put in the last questions there. You said that the first one, square, pentagon, etc., they are not periodic up to 5T. That's in the experiment?
On the experiment.
And you can to solve the Gross-Pitagevsky equation.
Yeah,
and you
so
can
we did the numerical.
You can go higher than 5T.
Yes, we did. So on the simulations we did.
You can
so
go, and you never see it.
Yeah, no, we never see it. So we did a numerical simulations for all the shapes we tried. Yeah. So I think we tried even more, here I list some, but we tried some exotic shapes also, and that were kind of symmetric just to see if we found something else. And the numerical simulations, we did it for very long times, and we didn't see any periodicity instead of the triangle and the disk.
There is just one small detail, probably.
Yeah.
I don't know how large the times are, but you see, evolving these types of equations for a very, very long time, it is very dangerous because there are numerical errors.
Yes.
That you have to make sure first that the evolution remains unitary, and that's probably these times are too large or not. You know, that's something that should be checked.
Yeah.
But, you know, I believe that
so
it's just a small warning.
Himself, that Dalibard himself, that did the simulations.
Okay,
so and I think he checked everything.
He checked everything.
We discussed.
So there is nothing for a very long time.
No.
Okay. Yeah.
For a very long time.
Experimentally and with the Gross-Pitagevsky
Yeah,
equation.
experimentally we cannot go much further than 5T.
Yes, I can understand.
But yeah, but numerically
okay.
we went further and we didn't see anything.
Rosario?
Patricia, I have two questions. The first one is, you mentioned within the open question that you should include this term that is going like 1 over R2 square. Why do you need to include that
1
term?
over R2 square? What do you...
There, interactions
Here?
with 1 over...
This?
Yes.
So this actually is, if we want to try to search for these breathers in other systems, so we can expect to have, since these two systems are also scale invariant, so both of them, they will respect the same symmetry, so they will be described by the same symmetry group. And if we see a breather in our system, maybe in these two systems there will also be a kind of breather for the wave function, which we don't know which is the shape. So I don't know if it will be a 3D square, 3D triangle for the unitary Fermi gas, for example, or if it will be another shape. But if it's linked to the dynamical symmetry, there will be breathers in these two cases for a collection of particles with interactions described by 1 over R square, and also for the 3D unitary Fermi gas, okay, if it's linked to the symmetry, to the dynamical symmetry.
Okay. So, and the other question, or perhaps a comment, so this relationship that made by Petrov, in which you have the effective coupling interaction in 2 dimensions, was derived, as far as I remember, taking into account the geometry of the space in which the collisions occur. So if the collisions occur in these pentagon or hexagonal geometries, why do you expect that you have to keep the same effective coupling interaction?
Okay. So I think what he says about the geometry of the collisions is actually that even if you are in 2D with the system, then the collisions happen in 3D. So actually, it's the condition for the weakly interacting regime. So the scattering length of your atoms is much smaller than the oscillator length of your strong confinement. So actually, these interactions, they do not happen in 2D. So it's not a 2D process, but it's still a 3D process with an atom that is strong confined in one direction. And this modifies a bit the scattering properties. But this don't, from what I know, this do not put any constraint on the shape of the 2D cloud in the 2D space. So you can have a harmonic potential, you can have a uniform potential in any shape you want, and this do not change this effective interaction term. But this will affect if we increase G tilde. So if we depart to the weakly interacting regime, yes. So we have the other terms on the scattering amplitude that will give us this quantum anomaly effect that was observed in fermions.
Any other question?
Thank you for the talk. It was very interesting. My question, I have two questions. The first one is, what do you expect when you increase the interactions from a weakly interacting regime to a more strongly regime? And the second one is about maybe if there is no periodicity for the square, pentagon, etc., is there a kind of quasi-periodicity so that the shape doesn't return to the same shape but like an exponential in the correlation function or?
So we didn't explore it too much into detail, but we can see that, for example, if we start with a square, it evolves and we see this diamond shape here, and then it looks like it tends to go to a square, but it's never anymore uniform, never. So if we look for the triangle instead, what you have is that it's uniform. So it really recovers the initial shape that you have on your cloud. Okay? So in the case of the square, you always have some edge effects and it's never anymore uniform. We didn't see it. But we didn't study correlation functions on this set of data. It could be interesting to study this too. And about the other question, actually we don't know what we expect when we increase the G tilde parameter, because all the formalism I used to describe this 2D gas is no longer valid. So we cannot use anymore a classical field to describe this system. It's true that you will start to see corrections, especially on the interaction parameter, G tilde, so it will appear a correction with a logarithmic dependence. But then actually we don't know if we go so much to very high G tilde, we don't know what we expect. Even the superfluid transition is an open question. We don't know if it will occur and how it occurs, because the BKT formalism is no longer valid once we increase this interaction parameter. So we don't know what to expect.
Okay, any more questions? No? Okay, I have one.
Yeah.
A very not smart one, but what happens if you don't use a equilateral triangle?
If it's not equilateral?
Yes.
It doesn't work. So we use a right square.
Okay.
And it doesn't work.
Okay, so it's
It's the equilateral triangle.
That's it.
Yeah.
Okay.
It's a very, and we tried the idea to try the hexagon is that it's two triangles, but it's not periodic. So it's super weird. We really don't understand why, but it's very robust in the numerics as well. So we believe it's true. We really see something that evolves periodically in time, and but we cannot explain.
Wow. Any other question?
Yeah.
And it is not clear to me, what do you see when you use the disk? Because you say it's probably periodic, but what exactly do you observe?
Can I just put it here, George?
Yes.
Yes. So we have, I have the set of images for the evolution of the disk, but pretty much what we will have is that it's no longer uniform. So if you look for the disk, so this is the experiment for the disk. If it opens, yes. Slow Windows computer. It will open. No? Oh, I hate this Windows. It's a mess.
Se você provar outro.
É. Posso abrir com Paint? Wait.
Haces preguntas muy difíciles, Andrés.
No, I was not prepared to show you. But so what we see is pretty much that it is never uniform. So in the numerics, it looks like it recovers a uniform shape, a uniform density after 2 periods. But in the experiment, it's never clear if we see it recovering the disk shape uniform. So we always have some edge effects or more atoms in the center, a higher density in the center, and it's never uniform. So it's not exactly the same wave function that we start with. So you see?
Yes.
Ah,
But it looks a bit here, maybe at this time, maybe at this time. Here it looks like it is a bit uniform, but it's never, if we calculate the overlap as we did before, we have a much lower value for the overlap. So all the images I showed you, the overlap were reaching 1, it was really close to 1. And here it's not the case, even though we can get mistake by looking to the images, you see. But here there is also always a kind of shadow in the edges. So we don't really, so this looks very uniform, but if we calculate in the end, it's never the case. And this is more or less the same with the numerics. So the numerics is a bit more clear. We see this kind of two...
Those images, if you look at the diagonals, they are...
Yes, so it should be the diagonal. You see that it's in bold here. It's in bold, and here it should be something like here, I think. This guy, and this guy. So it's a bit shifted, the images. So it should be, this is the 2 times the period. That should be the one we see on the numerics. But if we calculate the overlap from the experimental data, it's not clear. Even though if it looks quite nice by eye. So it's, yeah. Okay.
Thank you.
Okay. So if there are no any more questions, we can say thank you to Patricia. This is your certificate.
Oh, Fishiker.
And now we can welcome our next speaker, Professor Victor Romero. So, sorry?
I have 10 more minutes to begin, or
You can start as soon as possible, and then you can go slow. So while he's preparing his presentation, I'm going to present him. And of course, Victor,
this is good.
he got his physics degree at Universidad Autónoma Metropolitana here in Mexico City. Next, he got his PhD degree at the Massachusetts Institute of Technology, MIT, in Boston, the United States. And now he's professor, he's full professor at the Institute of Physics here at UNAM. And he's going to talk about correlation length in across the BEC-BCS crossover in a superfluid, in a fermionic superfluid.
Sí. Me tengo que tomar un medicamento.
Ah, claro que sí.
Me tengo que tomar un medicamento. Sorry. Okay. Thank you very much. Okay. Let me see. This laser. Okay. Okay. Good morning. Thank you very much. Thank you to Jorge for organizing this this workshop, this first workshop on macroscopic quantum phenomena. And as he mentioned, this is going to be another type of ultra-cold behavior, what I will talk about, which is about the fermions in this time. And this is work, what is this? ¿Será un micrófono por ahí? No. ¿Ya le bajó? Okay. So thank you very much. So the title of this talk is Pair Size and Correlations Lengths at the BEC-BCS crossover. And this is a work in collaboration with Juan Carlos Obeso Jureidini, who did his master's degree in this topic. Most of this, the work that I will tell you is in the archives now. It's being refereed still. It's not published. Hopefully it will be published soon. And this is a topic, the BEC-BCS crossover, that you will hear probably in two more talks at least. Jorge will tell you about the experiments and so on. What I will do is, this is a very theoretical talk. I'm a theoretician, and so this will be a very theoretical type of talk. I was thinking to put some pictures, but I decided not to do it because you will see real pictures of these systems probably with Giacomo and with you, I guess, at least with the two of you. Okay, and so this is a topic. The BEC means Bose-Einstein condensate, which is the Bose-Einstein condensation that we've heard about in the last many years, and Patricia just talked about this in rubidium 87, although in a two-dimensional system. And BCS stands for Bardeen, Cooper, and Schrieffer, which are is the famous theory that explains superconductivity. In the paper was published in 1957, and then they got the Nobel Prize by 1972, Bardeen, Cooper, and Schrieffer, and I will tell you about this ahead in my talk. And the idea of the BEC-BCS crossover, there are several authors. One of them is called Eagles and other people, but the most that I will base the work that I've been telling you today is by Anthony Leggett, who also got a Nobel Prize, but not for this, but for studies in superfluidity. It is a very famous paper of 1980. So the theory is very old. 1980, I'm sure that most of you were, I don't know where were you, but I was in college in 1980. And however, the topic is very common still today. There is a lot of work, theoretical and experimental, in this problem. And it happens that this BEC-BCS crossover is also not important in our field of ultra-cold gases, but in nuclear matter, and some people talk about this in the beginning of the universe. There are so many fields that now use this model as an explanation for what they see or what they have in their experiments. I will not talk about that. I will just concentrate in the very simple problem to make it as simple as possible. And so let me tell you this first with the pictures. By the way, I realize that my transparencies have very big letters, and it's because I typically give talks in seminar rooms where the screen is like this, okay? So I apologize if it's too big for you. It's fine, you can read it, without glasses. So this is a picture that I stole from the internet, and what I would like to do, as a matter of fact, is to, along the talk, is to explain to you this crossover, but go beyond. The purpose of the talk is not only to tell you about the BEC-BCS crossover, but also to go beyond, which is our work of Juan Carlos and myself, and also I should say Rosario Paredes was involved at the beginning of this topic, and then we did some other stuff that I will probably come back at the end. And so the idea is to tell you about some new results concerning the correlation functions of this problem and the correlations length involved, such that we believe we can give a more accurate, I'm not saying better picture, but probably a more accurate picture of this phenomenon. So let me tell you what the phenomenon is. It is a very cold gas, and the theory is at 0 temperature, but it's supposed to be a very cold gas of a mixture of two spin species of neutral fermionic atoms. So you have atoms that are identical, except that one is in the up state and the other is in a down state. And that makes them different. Okay, the indistinguishability is only between this and between this, but these two are different. So it's a mixture of half of the atoms are in this state and half of the atoms are in the other state. And so one of them is red and the other is blue, okay, just for a picture. But the beautiful part is that the interactions among the atoms can be tuned, can be changed externally, and Jorge will tell you how they do that in the lab. But you can change the interactions among the atoms, which is very strange to be able, now we're used to that, but the idea is that the atoms interact with whatever they can interact. But now from the outside, we can change the interaction. So that makes another way of tuning what happens in the system. And so in one extreme, we have what we call Cooper pairs, where the interaction is effectively attractive among the atoms. The idea is that the atoms, red and red, do not interact among themselves, blue and blue do not, but only interact red and blue. And that is correct. Is a good approximation, because the Pauli principle prevents atoms in the same spin state to interact strongly. So they only interact when they are in different spin state. So the model is that atoms, red, interact only with blue and blue only with red, but not among themselves. And this is a picture. Pictures are very dangerous in quantum mechanics, because this is nothing, no picture is correct in quantum mechanics.
You have to be very careful with that. But the picture helps a little bit, and these are called Cooper pairs. This was the discovery of Cooper. You know, the Nobel Prize was because Cooper had the idea of the Cooper pairs. That's why I call Cooper pairs. Bardeen was a super expert with a Nobel Prize already in his pocket. And he was an experimental that knew absolutely everything of the experiments and all the phenomenology of the problem. We're talking about superconductivity. And Schrieffer was a theorist, a very deep, advanced theorist who actually wrote the theory. The theory was written by Schrieffer. And he said in his Nobel report that he didn't understand a lot of the things, but he knew how to do theory. You know, this is nice for us. So the idea is that you can tune the interactions, and so in this extreme you have Cooper pairs. And there is another extreme in which the interactions are such that there appears a bound state, and so the atoms make a molecule, and because they make a molecule, now they are bosons. You have two fermions, now they make a boson, and now the bosons, because at zero temperature, they have a Bose-Einstein condensation of this part. But the interaction can be tuned completely smoothly, and you go through a regime that is called the crossover or the unitary regime, and this is due in the experiments through a Feshbach resonance. I will tell you not about a Feshbach, I will tell you about another resonance, but still there is a collision resonance that makes these intermediate states that I want to be sacrilegious. Is that correct in English? Sacrilego. I want to that I believe that this state is overrated. You know, from the thermodynamics, you will see there is not much there. There is not much there, and so, however, people talk a lot about this state because it's neither this, neither that. So it's something like intermediate. Yeah, it is intermediate, but as you will see, not much happens over there. Anyway, let me go on. So the purpose of the talk is to tell you how this state arises, which is in books already, but then I have to give it to you as an introduction such that you appreciate what we did, I hope, which is to talk about the correlations in the gas, okay? So correlations is always a scary word for everybody. So as I'm a theorist, and so what we do immediately is write models, and we write Hamiltonians. And so the system is described by n½ atoms of spin up that interact with n½ spin down atoms with two-body interactions. And so this is a typical Hamiltonian, right, that you have kinetic energy of the up atoms, kinetic energy of the down atoms, and interactions among up with down. There are no interactions up, down, down. This is the model, and it looks extremely simple. So, and we only want to calculate the ground state. We can't. You know, that's always say this in all my lectures and classes. We are very far from really understanding these systems. But we understand some stuff. So here it's written in second quantized form, and I don't want people that do not know about much second quantization. Don't worry, it will not necessarily be used. I just want to mention that this is the kinetic energy, and this is the interactions, and these are creation and annihilation operators of particles, and this function here is the Fourier transform of this. So working in second quantization is as if you were working in Fourier transform in some way, more or less, okay? But this is, I write the Hamiltonian because I have to tell you what is the model, but don't get worried too much about the details. So this is the Hamiltonian of the system. Although this is easier to see, we work with this one. And then the function here is in real space, here is in momentum space. And so what I'm saying is that we can, not we, theorists, we only change parameters, but experimentalists can change the potential. And let me just review what is a two-body collision resonance. A two-body collision resonance, remember, we are at very low energy because the temperature is 0. Therefore, momentum is the wave vector, is the momentum. H bar k is the momentum of the particles. And so you have two particles colliding. They have very small momentum. Okay? And so the collision must be seen quantum mechanically. And the collision in the center of mass framework, you see the collision, you learn in your quantum mechanics book that you have an incident wave that is scattered as with an spherical part times what is called an scattering amplitude. But the potential is like this. I want to insist that the potential that the atoms is, that the two atoms is in this form. It just depends on the distance, and it has 2 parameters, some depth parameter and some range parameter. That's enough for what we want. And so since the system is very cold, we can keep just scattering at 0 angular momentum, which is called S-wave scattering. And I will flash here a lot of equations. I don't want you to get hooked in the equations. So while I put the equations, but so they help me to say things. So the scattering wave is it is of this form. And so in S-wave, it becomes completely spherical. It doesn't have dependence on theta, and it is expressed in terms of what is called a phase shift, okay, if you remember from your textbook. And the phase shift, in turn, can be written in terms of a length. The tangent of this shift of the wave function is defined as minus AA, defining the scattering length. And so this quantity is very important because, among many other things, one, it gives us the form of the scattering wave, but it also gives us the form of the collision cross-section, okay? And it can be written very simply as 4 pi over k squared plus this term over here. And I want to insist that the scattering length is a function of these 2 parameters. So the whole collision is represented essentially by 1 parameter, but this parameter is a function of 2 of the parameters of the potential. Now, what is a resonance? A resonance is the following. This is very interesting. So this is your potential. And the potential here, I'm trying to represent that is shallow, that the U0 is small. So it does not have any bound states. And if you do the calculation, you find that the scattering length is negative. Okay? So the shift of the wave function goes as if it were far away. The collision happened. No, the other way. The collision happened closer, and so this turned out to be effectively attractive. And so the scattering length is negative, but it has something very interesting, that it becomes very large negatively as we move U0. In the experiments, they move a magnetic field. And so when we get to a particular value, U0, that's when the resonance happens. And it turns out that here, there appears barely a bound state. There's a bound state, and U0 is larger. And if I make U0 even larger, here, the bound state definitely appears. And this is this size over here. So this is the bound state that makes that the atoms become a molecule, okay, in the BC side. At this moment, you don't know why this is BCS and this is BC, but this is for the moment just to call, to make clear where this is going to appear and where this is going to appear. So we have a change of the scattering length, and there is something very strange because it diverges. And that's scary when things diverge. You know, you get scared because you think that something spectacular is going to happen over there. But if you see at the scattering wave cross-section, the cross-section, if A is very small, over here or here, then you can neglect k squared, and the scattering length is 4 pi a squared. So A is like the size of the atom. However, if you go at the resonance, that is also called unitarity, then A goes to infinity, its inverse goes to 0, and the scattering length is 4 pi over k squared. But k is going to 0, it's very small. So it is very large. So the cross-section is enormous, right? So even though the atoms interact with potentials that have very short range, they get scattered very strongly, right? And that's the resonance. But this is a problem in two atoms only, okay? Now we have to put this ingredient in the many-body problem. That is the one that we are solving. And so now we have to consider atomic collisions at very low temperature in the many-body problem. And remember, and you see, if it is very cold, then the wavelength of the wavelength of the waves that represent the atom is much larger than R0, okay? Because P is small, and therefore lambda is large, and so the range of the potential is much smaller than the size, the quantum size of the atoms, and therefore we can neglect the details of the potential. And the approximation is that the potential that was a very complicated shape like that now can only be represented by a delta function, but it's very crucial, the sign of A. If I is positive, it's a delta function that goes up. If I is negative, it's a delta function that goes down. And so all the interaction, complicated interaction, is represented in terms of this potential with only one parameter. The potential had two parameters, but now we only have one parameter. And this is an enormous simplification for the statistical physics. As a matter of fact, if we don't make these approximations, we cannot do essentially nothing analytically. Absolutely nothing we can do. We have to do everything numerically, and it is very hard to do if you consider the full potential. But this is valid only for low temperatures, and so that's where we are. And so our Hamiltonian now has, again, this is just the kinetic energy written in this compact form. This is the kinetic energy of a free atom. This is the interaction term, but now the interaction term is just a constant. It's not a function that was here before, but it's just a constant, and so we can do a lot of theory. And as a matter of fact, this is the ones that like a lot of theory. We can make maps of this calculation to field theory because of this approximation. If not, it will be very difficult to make field theory with the full potential. And the interesting aspect is that this Hamiltonian looks very simple. It doesn't look simple, but in words, it's simple, right? Because we have a constant interaction term. These are the number operators, so this is the operators that count the number of particles. But the interesting thing is that A can be tuned externally. Okay, that's, again, I repeat that again and again, so you get, this is 1957. You know, I wasn't even born. I'm old, but I'm a little less old than that. So what is the question? What is the only question that we can address? What is the ground state of this system? That's all what I will try to do. Zero temperature. What is the ground state only? Okay? In which we have a half and a half of up and down. And this is something extremely complicated, really. You see, if A is equal to 0, this is an ideal gas. And this is the ideal Fermi gas non-interacting that you learn in your textbook, that all the atoms fill the Fermi sea, right? You've seen this in your courses, and that's how we learn about the electricity and electronics and so on. So if A is equal to 0, the ground state is just the degenerate Fermi sea fill up to the Fermi energy. It's an ideal Fermi gas. This is textbook. However, if A is different from 0, no matter how small it is a superfluid. The state that I just saw, that I just told you, with all the atoms filling up the Fermi sea, is no longer valid. This is called, mathematically, a singular perturbation. Because you are used to that you have a system and now you have a perturbation, and if it is very small, then it is very similar. It's just a perturbation to the state. This is not the case. If A is very small, the problem is completely different. You cannot go from one to the other by making A going to 0. You don't get the other one. This is very interesting, and it is mathematics. It is called a singular perturbation. But you see, and this is, I'm going to be, for some of the experts, I want to bother them a little bit. Because this is telling me that the variable is not A, is 1 over A, right? So if 1 over A is the variable, if an A goes to 0, the perturbation goes to infinity. And so you cannot move from one to the other just by moving it very slowly, okay? And this will appear naturally. So it is a superfluid. I should say, a degenerate Fermi gas is not a superfluid. If you put A as small as you want, you can get a superfluid as we can see. Okay, so what is the procedure, the mathematical procedure? You know, I want to be, sorry, but I was told once, many years ago, I was an undergraduate studying, and we had a class with a psychologist, very strange. And he said, never apologize. Never apologize in your talk. The worst thing that you can do is to say, well, you know, I'm going to tell you some boring things. Never say that, you know. Never say that. You have to say always, this is very good, this is very spectacular. So people pay attention. If you say this is boring, people say, okay, they leave the room. So, but it's heavy. That's perhaps what I should say. It's some mathematics, and if you haven't seen this before, it looks heavy. But it is not. So what we would like to calculate, you see, this is for those that know statistical physics, this is the ground potential. But you can think that this is, psi 0 h, psi 0 is the energy, okay? Is the energy of the system, is the expectation value of the energy in this state psi 0. However, I have to fix the number of particles. I want that the number of particles is n over 2 exactly, and so I have to put a Lagrange multiplier, which is the chemical potential. Is one way to see it. And if you know statistical physics, this is the ground potential in the grand canonical ensemble. So the purpose is the following. BCS and Leggett, but BCS was the idea, but this is a very common idea in physics, is that if you are very smart, give me a wave function, make a variational procedure, I will tell you how to make a variational procedure, such that this quantity takes its minimum value, right? So you are looking for the best psi 0 to make this function to take a minimum value. I probably didn't say it. Psi 0 is the wave function of the ground state. You will tell me, why don't you just calculate it? The answer is, we can't. One simple thing would be just I sit down, I make all the mathematics, and I get the ground state of the problem. We can't. And therefore, we invent variational procedures. We find the best one, the best psi 0 that minimizes these functions, because thermodynamics tell me that this function must be a minimum in equilibrium. So I look for one psi 0. I will tell you what it is in a moment, and that's it, right? This is a very common way of doing physics when you don't know how to solve the problem. You find the best solution that you can, and the chemical potential adjusts itself to give you that you have exactly n over 2 particles up and n over 2 particles down, or the other way around. And only this is valid for 0 temperature. By the way, choosing the right wave function is a Nobel Prize. If you think something simple, it is not. Some people have got a Nobel Prize by choosing psi 0. BCS did it, Laughlin did it, and some other people have done this, and they find their wave function. So this is the wave function. It's becoming heavier and heavier, but it is not. As a matter of fact, this is not BCS idea. This is Shafrot. This idea was these guys, I think they were from Australia, of New Zealand. Australia or New Zealand is the same. They say the same about us. Brazil, Mexico is the same. They speak Spanish. They say that. No? Patricia? It's the same. So whatever. But these are people that live in the other part of the planet, that they got this idea, but they didn't find how to write phi 0, and so they missed the Nobel Prize. However, this is the correct idea. So what is the proposal? Cooper found, by the experiment show, that in superconductivity, the electrons had a superconductivity when they were pairs. When plus and minus electrons go together and move together in the crystal, that was the superconductivity. The experiment said that there must be pairs in the problems, that the atoms should get as pairs in some way or another. And so the idea is to propose that all the up atoms pair with down atoms, because remember that plus and minus, they don't see each other. They see only one is plus and the other is minus. So all the atoms are in the same pair wave function, right? However, since these are fermions, the wave function must be antisymmetric. And therefore, it says that if you expand this determinant, it tells you that the wave functions of the n atoms is products of wave functions of 2 atoms, each pair in the same state. This is basic always for these problems. All the pairs are in the same state, but it is a superposition. It's not a pairing of the two of us are a pair, you two are a pair, you two are a pair. No, it's all the possible pairs that we can do among each other and then make a superposition of that quantum mechanically. And so the first picture that I put of atoms pairing with someone else is false. This is quantum mechanics. It's a quantum superpositions of all the possible pairs and all the pairs with the same wave function. You see? So and this is the question is, who is this wave function? That's the whole problem. If you find who this wave function is, you solve the problem. And Shafroth couldn't do it. Shafroth and his friends couldn't do it, but they had these proposals. And now this is used a lot when people do Monte Carlo calculations and things like that. People use this again, and this is very important, but they didn't get it correctly. It was Cooper and Schrieffer, and they proposed this. So look at this. You can understand this. You cannot understand this. This is the same wave function, but in the other image, in the K way of seeing things. And Schrieffer wrote this, and he said that he didn't understand it. He said that, honestly, that he got the results, but he couldn't explain well physically what it was. So this is the form, and let me tell you first the form mathematically. Now, before it was phi 0 was the unknown quantity. Now we have two parameters, UK, VK, which are two parameters that are not independent. They must obey this because this function must be normalized, so they obey that VK squared plus UK squared is equal to 1. So essentially we have only one parameter here. There is only one parameter, but for all values of K, so it is a function of K, right? So instead of having a function phi, we now have this parameter. And this operator creates a creates a pair, but in momentum space. It creates a pair with a spin down and momentum minus K with another atom with a spin up, but with momentum plus K. So the pairing is atoms like this, but this has this momentum and this has this exact momentum. And this product is the superposition of all the possible things again. Okay, so this is another way of seeing. And you see, how is this related to the previous wave function? Very interestingly, the ratio VK over UK is the Fourier transform of the pair wave function. So they are intimately related, and so essentially this is the same problem, but in this case you can solve the problem. With the other wave function, you can't. Okay? You cannot solve it. And so let's go back to the procedure now. We know how the wave function is expressed in terms of these VKs, and so the derivatives, if it has to be a minimum, the derivative has to be 0 for all values of K, and this gives us this solution. This gives us that UK and VK are this function, plus minus, plus for U and minus for V. However, there appears a new variable here. So VK and UK depend on the chemical potential, the energy of each atoms, of each free atom, and a new quantity that is called the gap. Okay, and I will not say much except of the following. And this explains why this is a superfluid. It turns out that you're in the ground state, the system is in the ground state. But if you give it a little bit of energy, you excite the ground state. Okay? And so the gap is the minimum energy that you need to excite the ground state. If you give to the ground state less than delta of energy, it will not notice that you give energy to the ground state. You have to give this minimum delta, and that's why it's called the gap, because it's a gap. In Spanish, we say brecha, which is not correct, right? Brecha is where you walk. It should be, Rafael Barrio argues a lot about that shouldn't be called brecha, but we say brecha. So it's the minimum energy, and that's what is called the gap. And it means that if you are at a temperature, KT, smaller than delta, you cannot excite energy from the system, and so it is a superfluid. It will not get excited, and therefore it will not have viscosity. It's complicated, but that's the explanation. So the fact that there is a gap here is explained that this is a superfluid. In the questions, if you want, I can go back to this if it's not clear. Probably it's not clear. But it doesn't matter at the moment. It doesn't matter because the only thing is that I solve the equation, but in terms of something that I don't really know. But I can solve it self-consistently. Okay? So I have a solution for my problem, and then I can prove now from the previous solution, there's some algebra here, that I can express the scattering length in terms of the chemical potential and the gap, okay, which is expression over here. And also I can express the density, the number of atoms per unit of volume, as a function of the chemical potential and the gap. That means that if I know the density of the gas and I know the scattering length of the problems, I can solve and find the chemical potential and the gap. So this intermediate quantity can be found. It's two equations with two unknowns. We like that, right? We like the two equations, two unknowns. And so this solves all the thermodynamics because this gives me how the chemical potential and this quantity gap depend on the parameters density and scattering length. And say temperature, we are at 0 temperature, okay? So we don't have a problem. And now I put this second line over here because I want to tell you a story that it is shocking to me. Leggett wrote these solutions in 1980. And since then, there have been probably not thousands, but hundreds of, probably 1,000 papers, more than 1,000 papers that have written these equations. Thousands of papers. You know, I might exaggerate. 1,500, hundreds. Okay. I mean, this has thousands of citations. So it means that there are thousands of papers. And Leggett wrote this equation, and Leggett wrote this equation, and he couldn't solve them. So he only solved the two extremes, the extreme of BCS and the extreme of BEC. And he said, in the middle it can be solved probably. And then a lot of people later solved this numerically. And every student that I have had that has worked in this problem since 10 years ago have solved these two equations numerically. With Mathematica, it's simple, right? However, even from about 20 years ago, probably, it turns out that this can be written analytically. These two equations that have been written thousands of times have an analytic expression, which are this and this. I learned this a few months ago. I've been working with this for 12 years. And I discovered, I have seen it, but I always thought that it was probably an approximation, and, because it was in one of two papers over there. Okay, there is this guy Strinati from Italy, who's very good. He has some expressions like this, and there is another people somewhere there. But it is very obscure how they find this equation, how they find this solution. By the way, who are these P's? These are the Legendre functions. So that's why you have to take math, right, to learn this. These are the Legendre functions of order 1/2, 3/2, strange. And Z is this function, is just this parameter, is mu divided by the sum of this. So you can solve this, you can put this in Mathematica and say solve, and you find you don't have to do any integral or anything. You just put solve and gives you the answer. Something that I put the students, and many students in the world, that made programs to solve this. But the thing is, why people didn't write this? Well, Leggett didn't know. Of course, he didn't know because in his paper he said, probably it can be solved in the middle, but I don't care. He only solved for C near to 1 or C near to +1 in another language, but it's equivalent. And there, we found one paper that said that in order to do this, you have to use field theory dimensional regularization. And when you hear that, you get very scared because you have never heard in your life what is, how did I say it? It's field theory dimensional regularization. That you have to change the dimension of the space and then take a limit. And he said, if you do this, you can get this stuff. It's not true. You can do it. Of course, you have to write this first in the thermodynamic limit. This is an integral, and you have to be smart how to make expansions, and you make changes of variables, you make expansions, things that theorists love, no? Especially theories of my age, that we like to do a lot of algebra. So we feel that we're doing something important when you spend 6 hours to write one equation. And it is not true. It is straightforward. It is something that you just have to, to sit down, take a cup of coffee, and think, and then use a book that is the Bateman collection. Anyone You, Rocio, know the Bateman. Of course, Rocio knows, and Carlos know the Bateman. But the rest of you, you don't know what's the Bateman collection. It has this spectacular name, the book that is called Higher Transcendental Functions. Oh, Jackson knew about it. Yeah, of course. You see, this is lost knowledge. It's terrible. These were books that were an effort of Bateman and a full team in Caltech or in one of the Californian universities, you know. I'm giving them credit, I don't know where they are. This was a big effort in the 40s and 50s, and they ended up with 2 volumes like this. 3 volumes? No, it's 2. 3? Okay, probably 3. Higher transcendental functions with lots of tricks of how to do integrals and expansions and so on. And 70 years later, nobody cares. You don't care. You go to the computer, you put Wolfram, and you hope to find there, which is wrong many times. Using this book, I realized that Wolfram has the gamma function and the beta function is wrong. I wrote to them. You know, you have to be careful. It doesn't have the ifs. You know, many of the formulas have if the argument is such and such. It doesn't have that Wolfram. So very dangerous Wolfram sometimes. So there I found the trick. And it turns out that this is essentially the kernel. This is the kernel of these polynomials. Unbelievable. So you have to expand, and then it's beautiful. You have to expand, and then integrate by term, identify a beta function, and then identify that the sum is a hypergeometric function. What else? Everything is a hypergeometric function, right? You know that. So I'm writing here because we are very proud of this. It took for us several months, but we finally found that this was straightforward to go from here to here. You just have to be to grind, and so I can give it now as a homework next time that I teach this class. But a picture is better. So this is the behavior, this is the chemical potential, and this is the gap. And you see the variable is 1 over KFA, and you can see it from here. Here is when you see that it's a singular. If you put A equal to 0, this diverges. So this is the singularity. So there is really a singular perturbation. You cannot just put, but you can put A equal to infinity, and this is 0. So the crossover is here, and nothing happens. They don't even cross there. They cross before. I always thought that they cross at this line, but no, they cross before. It's very disappointing. And so you only see that mu does like this, and the other does like that. And here, mu, I'm introducing reduced variables. I have what, half an hour? Yeah.
3 minutes less than that, 27 minutes.
I have 28 minutes. So this is the Fermi energy associated to the problem. The Fermi momentum is nothing but the density. It's a way to write the density. So we can write the gap and the chemical potential in these units. This is how it is written, the graph. And the BCS limit means that you are in this extreme, and the chemical potential is essentially 1, which means that it's very close to the Fermi energy, but it's never equal to the Fermi energy. It goes asymptotically, but it is never in the free energy. And the gap goes to 0, very peculiar, but it's a very famous formula. You know, the gap goes to 0 with an exponential here, that this exponential is going to 0 because 1 over A is going to infinity, to plus infinity, this part. So when you cross the line here, this is the state, and over here, it is not easy to see that you get these molecules. There are tricks to see that in the BC size, where the chemical potential is negative, but very deep negative, and the gap is very large, you get this state. So what I will try to do, here's the BC limit, how it diverges. Again, it's always the variable is 1 over A. It's never A. It's 1 over KFA. And so here is 0, and so there are in universal thermodynamics, for instance, what you mentioned before, there are other interesting aspects here, but not the crossover. The crossover doesn't really register much. So up to here, this is essentially what you find in books and in many places. As I said, with this, it's hard to understand that you are seeing this picture. So what I will try to do is 2 things in the rest of the talk, to try to convince you that you can see this picture, but something else, which is what Juan Carlos and myself did in the last year or so. Okay, so I call this the spatial structure, which is the size of the pair and the correlation lengths, the density correlation lengths of the problem. Remember, if I know Vk and Uk and I take the Fourier transform, I have the pair wave function, okay? But now I would like to calculate something a bit more sophisticated, which are the correlations between plus minus and plus plus, okay? Correlations always tell you that how independent is one part of the fluid with respect to the other. You see, if the correlation is 0, that means that all the small parts of the fluid are statistically independent, such that if you do something here, the rest of the fluid does not know, right? However, if they have correlation, it means that if you do something here, at least in the neighborhood they know, and then far away they don't know. So it tells us how the fluid becomes more statistically independent with respect to itself locally, okay? That's what it measures, the correlation length, although it has a lot of other things that I don't want to get involved. It's a very powerful quantity because it goes beyond thermodynamics. You cannot do this if you don't do statistical physics. Thermodynamics will not give you this information. So this is the first powerful answer that statistical physics gives you to the problem. And so I just repeat, it tells you how one part knows about the other. And so this is the plus minus, the minus plus, and the minus plus, I want to say more things, but I will leave it like that. It has this form, and these G's are nothing but U and V. So the plus minus is the product, UK, VK. The pair wave function is VK over UK, and plus plus, which is equal to minus minus by symmetry. Plus plus is the same as minus minus, is just the Fourier transform of VK squared, okay? So if you want to know these correlations, you say you only have to do a Fourier transform. And people have said this for 20 years already, maybe more. You have to do a Fourier transform, and there is not much else to do, except that we have a technical problem. And you see advancement in experimental and in theory, experiments and in theory, it's always by a technical solution of something, right? Once you can solve one thing, you can do a lot of things. So let me give you just a flavor of the problem. So you think, what is our contribution? Our contribution is to do these integrals. It boils down to do the integrals that I will tell you. For instance, let me tell you about the wave function phi 0 of r. Vk over uk, you can demonstrate that this integral in 3D can be written like that. It's a Fourier transform in one dimension. It was 3D, but because of the symmetry, it is a Fourier transform in 1D. So you say, put it to Mathematica, right? And just say Fourier transform, or use a fast Fourier transform, an FFT, we say. Well, it turns out that it's not that easy because the integrand decays very slowly. Decays so slowly that the integrals are very inaccurate, and you can only get to small r's. You cannot go to very far r's unless you had a super computer, and people always stop and say, come on, I have a computer like that, that's enough. And I can see how it goes, and we speculate. And you cannot really calculate the Fourier transform, the full structure of the Fourier transform, because a small technical problem. So FFTs are not good to give this, and you see a lot of papers where they calculated some parts of this, but they stop and they don't say much simply because there is not an accurate integral of this. And so what we did, this also, I want to show off. We are very proud. We did this. This is also theorist stuff. 19th century theoretical physics. So this integral is from minus, in the complex plane, this integral is from minus infinity to infinity, right, this integral. But it turns out that the integrand has 2 branch cuts and 2 branch points. And so you can deform the contour, and by the Cauchy theorem, the integral of this contour is 0, and therefore the integral of this is minus the integral of this over here. And if you do that, you get this. And you say, come on, this was easy right now. This looks terrible. It looks terrible, but it isn't, because it has this term. It has an exponential term. And every time that in an integrand you have an exponential, it converges like that. So this was just a technique of using FFT. We just do, well, not we, Juan Carlos, integrates this very simply, not very simply. He writes a program to write this integral, but this exponential And we can put any R value that we want. You know, there are some technical aspects that we are very proud, but we were able to be able to extract this phi 0 essentially for all values of R. And this tau 0 over here is an integral from tau 0 to infinity. This is the position of the branch points. This is not important. The important thing is that we can do the integral because of a theoretical trick. Oops, it doesn't look very good. These are just some examples. 1 over kf equal to minus 5, which is in the BCS side. So we see oscillations of all the functions. What we see is that the three quantities here have an exponential decay, but they oscillate, okay? And they oscillate at different frequency depending where you are in the crossover. This is the crossover when 1 over kf is essentially 0, and this is the BEC part, and this is the BCS part. And from here we got a lot of information. From here we have the form of this is the wave vector, the wave functions of the pair, and these are the correlation functions. There is a lot of debate in the literature. In the literature, many people, experts like Strinati, say that this is the wave functions of the pair. Ketterle says that this is the wave function of the pair. And this is a correlation function, sorry. You can call it whatever you want, but this is a correlation function. It is not a wave function. But they say that. But you see, there is one thing. It's because there are, in some extremes, this is the easiest to calculate. If you do some approximation, you can calculate this and get a lot of information. But as you can see, they are really related to each other. Because they only depend on dk and uk. Which are the variational parameters of the BCS theory. So this is our contribution, but the idea, this is just only a few pictures. What we really do is to analyze this for all values of R and so on, and this is what I would like to tell you now. So these wave functions and the correlations, their square can be fit very, very good by a function like this, something that decays as 1 over R squared, and an exponential, envelope, muchas gracias, an envelope, an exponential envelope, and an oscillatory function, which is periodic. It's not a sine, it's not a cosine, but it's a periodic function. And that it has a characteristic wave number and a phase. So the three of them can be written like this. So these three quantities are small, and what we did is to extract them. And here is a complicated picture, but I will show it twice. So the red line, the solid red line, the solid blue line, and the solid green line are the decaying lengths, the exponential decaying length. And you see they behave these two behave essentially the same. However, this one has a little bending over here that we thought at the beginning it was numerical, it is not. Okay, so this is the exponential. And see something very important. In the BCS side, here, we find that the decaying length goes to infinity. That means, if the decaying length goes to infinity, that means that the exponential is equal to 1. And you only have oscillations, but these oscillations remain for a very long time. That means that the wave function is huge. That's BCS. Those are Cooper pairs. On the contrary, if you go to the BEC part, the exponential function, the exponential length is very small. That means that the exponential term dies very quickly. And that means that the wave function is very small. And that means that you have pairs. Right? So this is the explanation that you have molecules on one side and you have Cooper pairs on the other. And these are the correlations. I'll go back to that. And so this more or less explains this picture. Now the other is the wave vector. This is very, you calculate these things and you have to give a talk. You even write a paper and then say, I don't really understand this. But you come and wave your hands. We find that the three wave vectors, that they oscillate exactly with the same wave vector, probably because the model is very poor and it doesn't have many parameters to combine, and it says something very interesting. It says that these functions, the three functions, they oscillate essentially with the separation of the atoms, right, in the BCS part, and the wave vector goes to 0. That means that the wavelength goes to infinity. So the next time that the wave function oscillates is very far. It's getting very, very far away, okay, on this part. and they are exactly the same. However, the oscillation, and so this says that I will go back to that later. And this is the difference of the phases. And there is something very interesting. The phases of the oscillations, of the correlation functions, of the correlation functions and the phases of the phase of the wave function, the correlation functions, they oscillate exactly out of phase. So they oscillate like that, right? So that means that if you are an atom like that, on the average, you see closer to you atoms of the other pairs like you, then of the opposite, then of the opposite, then of the opposite. They change like that. There is like a nested structure that for me, I still don't understand, but it's there. It is there in the theory. So this tells us something about the structure of the correlation function that we still do not know very well, but it says that you have a nested structure that I will go back to my last transparencies. I'm almost finishing. I don't know what happened here, but so now how do we calculate the correlation length? What is a correlation length? And this also is debatable. I mean, people invent quantities to measure things, and this is the second moment. If you have a distribution rho bar, which is the density, probability density, and the correlation functions, the integral of R squared is the second moment, right? It's the second moment of the distribution normalized. And this is a definition of a correlation length. It's a definition. It's a length associated of how quickly R squared is weighted by the function. How if it is large or if it is small. And I'm showing off, of course. I will just flash this. But we were able to calculate all of this analytically. We're very proud of that. This one, nobody's seen them before. Say, who cares? Well, but nobody's seen it before. These ones, Strinati calculated them, but not with this variable. He does something very complicated. He instead of using Legendre functions and hypergeometric functions, he does something equivalent, and it's an integral in the complex plane. But it doesn't matter. At the end, I checked his expressions are different than ours, but then we checked that they were exactly the same, including the 1/8, the 3/8, everything was. And you see there is one other thing. These are completely analytical. There are no reduced quantities. So we are proud that we were able to calculate this analytically, and therefore we can plot them. And those are these functions. These are really exact calculations. These ones are fit. This is a fit, this is a fit, and this is a fit. And the oscillations are fit. But this one is not a fit. The dotted lines are not fit. And now the three of them are very different. This is very interesting. And this adds to the understanding of these pictures. It says that even though that the wave function in the BCS side, when you have Cooper pairs, the exponential is not playing a role. That means that the wave function keeps oscillating, right? It says that because it decays algebraically, on the average, the size of the pair is finite. And this is a number which is, I'm going to write it. It's a square root of 21/2. But it is. This number over here is a square root of 21/2. And so it says that the size of the pairs on the average remains constant. However, because the distribution is algebraic, it means that there are pairs of all sizes. There are small pairs like this, and of all sizes. It's not true that all the Cooper pairs are very large. No, it's not true. There are very small pairs also, at least within this theory. And the average is a constant. Now, this is very terrifying. For me, these two. And on the other side, it goes to 0 because you expect that here there are molecules, and therefore the size of the wave function is very small. The size of the pair is very small, which is what we expect in the BCS side. At 0, nothing happens. Well, you could say that at 0 is where the break almost happens, but it's not very clear. But these two, if you look at this part, it says that the correlation length of the fluid in the BCS part, when you have Cooper pairs, is very large. People say that when we have the resonance, the correlation is a very correlated gas. It's not true. The more correlated gas is the BCS. And that's why you cannot turn it off. It is either different from zero or is zero. So, and I think this has consequences for the experiments. So it is very highly correlated in the BCS part. And in the BEC, these two decay in the same way. And this is in agreement with people that say that this function, that this correlation function is the size of the pairs. Yeah, it is the size of the pairs, but only in the BEC part, not in the BCS. Only in the BEC is the pairs. And this is very nice, because it says that the plus correlation function dramatically goes to zero, because they form pairs of molecules, and now they are like an ideal gas. And therefore, here we have a plus and minus, and you have a plus and minus. This one does not know anything about the one, it's totally uncorrelated. So it is an uncorrelated gas of molecules. That's an ideal Bose gas. No? It's very nice. You can see it from here again. So this calculation was a little bit difficult because of the numerics. No, the numerics was difficult, this one. This is just simply evaluating the function. And so let me try to sort of wrap up. I'm doing well, right? So I hope to give you a flavor that, not with our work, of course, but with the work of many people, but we had added to this knowledge. That's our purpose. We are not claiming that we are solving anything completely new, except that we are able to calculate those correlation functions better than before. That's our claim. So what is the picture at the end? The picture at the end is that the BCS, this quantity, which is the important quantity, goes to minus infinity. This one is the one that diverges. And the exponential decay length diverges. However, the average pair size goes to a constant, which is a square root. This is divided by kf. No? It's square root of 21 over 2 divided by kf, the Fermi momentum, which the Fermi momentum essentially is the separation between the atoms. So it is a little bit higher, like 3 times the separation of the atoms. That's the average of the pair size, although you have sizes of all, you have pairs of all sizes. And so you have to keep up with this full determinant. However, if you go to the BEC part, now is when this goes to plus infinity, and now everything goes to zero. And that means that when you calculate averages, this determinant collapses to the diagonal only. Actually, it collapses to any combination that you want, but since they are you cannot distinguish one plus and minus, you can use the diagonal. And so this is the wave function that remains when you are in this limit, once you calculate average. But this is a BEC wave functions in which all the pairs, these are now molecules. All the molecules are in the same state. That's BEC. Okay? This is this state over here. This, I think, some people talk about like this in some papers. But finally, this very strange pictures. I did it last night. I was very tired. I didn't know how to make it. And let me see if I can convey what I see here. Something that is new, something that you couldn't see in other papers. This is supposed to be the oscillatory structure on the average that sees a up atom. Okay, this is the up atom, and these circles means the probability of atoms. Of red and blue atoms. And so the oscillation is small. It's not that small. It's of the size of the separation of the atoms. This is the correlation, the oscillation of the correlation. But this is multiplied by an exponential decay that goes to zero because the correlation's lengths go to infinity. You see, if the correlation length goes to infinity, then you are correlated at very long distances. And so you can neglect the exponential decay. Okay? The Cooper pairs, their size goes to a constant, but the correlation's length all diverge in the BCS part. At unitarity, it turns out that the 3 of them are very similar. They are the order of 1, which means that they are of the order of the separation of the atoms, which is a lot. They are correlated. I mean, they are indeed correlated, except that this is more correlated than this one. And in the BEC, the oscillations get very far apart, and in the very limit, they just simply disappear. However, now the exponential decay is extremely fast. That's because you have a lot of molecules that do not know among each other, except that they are all bosons, and so that's why they Bose-condensate. And this is the way they go. I mean, these limits people knew, of course, right? Because you can calculate the limits without doing all the mathematics that we did. You have to be smart and calculate the limits, but we have, of course, all and this oscillatory behavior, we believe, is new. So this is my last transparency, but I want to say something else, and with that I will finish. You see in the experiments, as you will see later in Jorge's experiments, the clouds that they do in their experiments, they do experiments with lithium-6, and he will tell us in detail how you can go from the Bose-Einstein condensate part to the BCS part in the experiment, how they do it, how this change is made with a magnetic field, okay? And it turns out that when they are in the BEC, you can see the condensate. I should have brought a picture of yours. I have it over there, but I cannot find it now. So you have to see the condensate. And as I heard from the people here, from the students and from Jorge, from Jackson, and from many papers, that when people move to the BCS part, it becomes very hard. So it's easier to be here, it's very hard to be here. And there is something connected, I believe, that we should pay more attention to this fact. I mean, it looks like everybody knows this, yes, but if the correlations are long, that means that you cannot break the system into small parts that are statistically independent. And therefore, statistical physics fails. Statistical physics, the trick of statistical physics is the thermodynamic limit. That means that if you have a correlation length of this size, then a system of this size is in the thermodynamic limit. If the correlation size is this size, then go to a system like this. The thermodynamic limit always saves you. And in the limit that the correlation length is 10 kilometers, okay, put the ocean. You always win when you do theory. But in the lab, that's not true. In the lab, the system have a finite size. And so I would like just to throw the idea that an additional complication of the BCS part is that probably the correlations lengths are so large that the system in the BCS part is a mesoscopic system. It's not macroscopic. It is macroscopic in the BEC, but in the BCS probably is not macroscopic. It's probably mesoscopic, and that's why it's so difficult to deal with it, because one is dealing with an image that gives you thermodynamics, that gives you the thermodynamic limit, but in reality probably you have a more interesting problem. Now, more difficult perhaps, but probably more interesting, because it's like you are doing nanoscience. You know what I mean? The people that do nanoscience are very proud that they have a system so small that nothing applies. That's why they have a new field. It's not microscopic, it's not thermodynamics. It's something in the middle, and it's called nano. Nano things, nanoscience, right? And they say they have new physics. You have a lot of people in this institute that work on that and in the world, because that's mesoscopic systems, and so we don't have really good theory for mesoscopic systems. And probably the systems in the lab may be in that regime. You should think about it. We did some calculations. Juan Carlos showed to me some arguments that how the local density approximation fails miserably. It should fail terribly. And so if all the theories are with the local density approximation, then we're in trouble. We have to do something else. Okay? And so, thank you very much. That's the archive paper.
Thank you, Victor, very much for this very nice talk. We have time for a few questions.
Giacomo, where were you?
I was here.
You were here.
Always here. So, nice. Thank you so much.
Yeah.
I have one question related to which is your, if it's possible to ask this, the physical intuition for which the Cooper pair size,
Yeah.
average,
Average.
goes to a constant. first. And second question, I would say that when you say that the pair size in the BC limit goes to 0, you go with A equals 0. Yes, the limit is for A equals 0, okay, if A going to 0.
In which? In the BEC?
In the BC, yes.
Yes.
So because you go to 0 scattering length, this is your point? Or because
No,
I
no,
would
no.
say there is something that I don't understand. So the pair size cannot be 0. So the pair size should be related to the scattering length. Like, I mean, is a bound state, so cannot be 0 physically.
No, I didn't have time to go into full detail. Thank you. Your question is very good, especially on the side of the BEC part. It is true. The size of the what we're talking about here is how the correlation length and the I should put it. Yeah, this thing. This over here. Yeah, of course, it never goes to 0. It gets, sooner or later, it goes like the scattering length. You are completely right in this part. That's the size of the size of the molecule. Yeah, no, that's for sure, and that becomes, that remains. I'm not saying that I'm changing that picture at all. No. And so that answer a little bit?
Yes, but and about the Cooper pair size.
Ah.
The VCS, why, I mean, which is the physical intuition for which the average is going to a constant K effect to the maximum? So because
No, let me, yeah, no. This is part of the debate. Because I don't have the time and I don't want to tell you there is a big debate about it. It's not clear what you mean by the pair size, right? And I think that, so if you look at Strinati, he says that this is the pair size. The pair size is this curve that is over here. So and also Ketterle, I think. They talk about the pair size of this function, while they call this the BCS function, but they don't want to call it the pair size. So you say, okay, so let's look at the three pictures better. I think that the idea is to look at the three pictures together and get an overall picture of what you are looking at. And so the wave function that enters the big wave function has the decaying exponential terms goes to 0, but is lower than these ones. Is lower than these ones. But you see, if you lose, it goes slower, and therefore, that makes that when you calculated this quantity, which you see is arbitrary, is this. This is quite arbitrary. Why is this the size? If it is a Gaussian, of course it's the size of the Gaussian. We take our intuitions always from Gaussians. If it were a Gaussian, this would be the width of the Gaussian. But if you have something that is not a Gaussian, that is algebraic, then there are algebraic functions that this quantity, that quantity goes to infinity. That means that it's decaying algebraically. That's all what it's saying. Okay? And what it means that it decays algebraically, it means that you have all sizes. This is like critical phenomena. All sizes count. That's really the physics. And so what I would like to think is that this quantity goes to a constant for the wave functions, which means that it has a finite size, the wave function, but it doesn't mean that that's the size of the pairs, because it's only the average. Okay? So you have pairs, but the thing is that you have pairs of all sizes. I think would be a better way to say, instead of drawing always big pairs, you should say, no, there are some small, some intermediate, and some very large. While in this part, they are just all very small, right? And so in the middle, they all have the same. So it is an interesting state because everything is of the same order of the separation of the atoms. So that's highly correlated also, And the average gives you, of course, the same number. It gives you.
But if you want to differ, but the unitarity, in fact, the scattering length doesn't play any role.
No.
So it should be just Fermi energy and.
No. It's not that simple as to saying that it plays a role. It plays a role because if you move it, when something doesn't play a role, let me ask you in a very bad way, mathematically, it's a point. It is not It is not a set of measures, it's a set of measures zero. It's different when something is always zero for all the things that you do. It's just a point. So it doesn't really count as a point, the fact that it's zero there. You have to see in the neighborhood. And so in the neighborhood, change the sign. You know, the scattering again changes sign. This is only a point. If you have a lot of variables with that equal to zero, that's a different subject, right? For instance, if you move temperature now, and you know, if you move temperature, then you can have a universal gas as a function of temperature, but not as a function of these variables. More or less?
Carlos?
Typical correlation lengths in superconductivity would agree more with your middle graph in the sense that the BCS superconductors correlation length is about 1,000 angstroms, and high temperature superconductors that should be more like BEC systems have a correlation length about 10 angstroms, no? So the middle graph.
Yeah, but there you are not in the extreme in which A is essentially zero. A is a finite quantity. The effective A is telling you more that what is the effective A of those problems. And so if you look for an effective A, you would say, it's something like this. This is the mathematical limit in which you would take it to the extreme. But if you have a real problem, you look for your A, and you say, okay, this is the correlation length. So it's answering more like that. Yeah? I mean, I'm not saying that the superconductors are here. No, superconductors might be here. And that's, if you are somewhere here, I would tell you have to keep the whole determinant. And so it's a BCS state.
Yes.
It is not this extreme. We got to this extreme because we were able to solve it analytically. But now it should be, you can solve it analytically everywhere, at least for this problem. It is more like a way of talking about the problem. That we say BCS is only over here. No, I would say BCS is the whole thing, except that over here it looks more like BEC. You always have a determinant, even over here. I mean, you never have bosons. This is very important. Never you have bosons. You have things that behave as if they were bosons, but they are never bosons. You're always dealing with fermions. Terhar said that. I didn't say it. You know who's Terhar? The Dutch guy?
I think.
Yeah.
I wouldn't.
You don't agree?
He can make mistakes.
Yeah, me too. But I'm on this side now. So I'm allowed to say
Diego?
things.
So, if I understand, you did this calculation for an infinitely
Juan Carlos did it, but both of us.
Well,
Yeah, this is
an infinitely extended gas, no, with n particles, but
it is a thermodynamic limit.
is it that the thermodynamic limit? So,
All these functions, everything that I write here is a thermodynamic limit.
so in the next picture, yeah, what would you expect if the size of the cloud is finite? As you mentioned, in the BCS side, we would expect BSR.
Every time that the correlation length it gets near the size of your system, you are in trouble. You start to have troubles with all the formulas that you use from thermodynamics because they always assume that, I mean, you don't take the limit of the scattering length going of the correlation length going to infinity. Take this one, and say, okay, this one is 10 times the size, the separation of the atoms, right? So you better have a system that is 10 times that. And then you can use all these formulas to explain what you are doing. But if you have a system whose correlation length is of the same order, you are in trouble. It turns out that in water and the air and everything, the correlation lengths are extremely small. They are angstroms. That's why we never care. You can have a droplet of 10 to the 4 atoms of air, and that's macroscopic because the correlation length is angstroms. Is the separation of the atoms. Okay? However, if you go near the critical point, the correlation length is so large that you have to have a system larger to study in the lab. And that's why the experiments can never touch the critical point. And so the experiments can never really touch this point because it is in infinity. The experiments will always be somewhere here, right? Then you better have a system that is bigger than this size. That's all what I'm saying. That's how you should use thermodynamics, or results that are based on thermodynamics.
How would you expect to change the phi 0, for example?
I don't know. No, this calculation, to be honest, people, we try to do what is called finite size corrections. But my opinion is that most of the finite size corrections, I'm very critical of many of those, is to take formulas of statistical physics and cut the number of atoms by hand. You are messing with it. You cannot just go to the formulas and say, I'm going to put the sum that goes to infinity, I'm going to cut it. It's your problem, you know. So I think that we do not really have mesoscopic thermodynamics yet. People in the field of nanoscience, they were hoping for that this will give them an opportunity to explore science in the intermediate regime. It's not atomic, it's not macroscopic, but computers. That's the only thing that we can do. To use computers, perhaps. I wouldn't know, you know. I will be cheating if I tell you that I know. Thank you very much for your question.
Okay, maybe we have time for one more questions.
You
Okay,
want to fill up?
Giacomo, please use the.
Do you think that the extension in 2D is possible?
The what?
In 2 dimension, can you extend this?
I don't know. Is there someone that has written the BCS theory in 2D? You remember they have a lot of problems with the scattering length and things like that. It's not trivial to go.
It's very complicated. Probably Strinati has attacked this, but I don't know, because probably I don't know if everything then becomes like analytical, like you said.
Yeah, probably you have the symmetries in 2D that, but first you would have to write the BCS theory in 2D, which I don't know. Yeah. You have a problem for your PhD. Right, to the BCS theory.
Okay, so let's thank Victor again.
Thank you.
This is your certificate, Victor. And we have the lunch break now. We will be back at 3:30.